So in the previous video, we'd ended off by assigning each of the 2,000 people in the biofam dataset to one of 5 clusters based on how dissimilar the sequences of family household formation or family trajectories were. And in this final video, I'm just going to take you through some of the possible plots that could be used to visualize sequence data in order to help interpret what those 5 clusters mean. I should say that this is only a selection of some of the possible visualizations. The Treminer user guide has a far more detailed discussion of all of the possible variations that you can use. The first the first plot I'm going to go through is called a mean time plot, and in essence this gives you an indication of how much time on average did the different clusters spend within each of the possible states, family formation states. So if I run this, the function, the mean time plot function, calls in the sequence object and it produces a visualization that's grouped by our cluster membership. And here's the visualization. So the height of these bars is a representation of the average time spent within that particular state. Time relates to, well, in this case, years, because our states were measured at each age, each year, between the age of 15 to 30. So as an example of how you'd interpret this, cluster 3 is a fairly easy cluster and unique in that the majority of the majority of time within this cluster was spent in state 0, and in cluster 1, for example, people spent roughly, equal amounts of time in state 0 and state 6. At the moment, this is the labelling of the states makes this pretty difficult to interpret, but in the worksheet I actually show you how to attribute values and labels to the states, which makes interpreting these visualizations a lot easier. I'm just going to move on to the next visualization. And I'll just run it and explain it. Again, it uses the same process of splitting the visualization by cluster membership. This is a different approach. So it shows you, essentially gives you a breakdown of what that cluster, what states were that particular cluster in during each of the time periods that are measured in our sequences. So it's essentially just a stacked bar graph multiplied by however many observation points you have. And it's quite useful for understanding general sort of migrations into certain states. So as an example, the majority or all of the people in cluster 1 were in state 0 when they were 15 years old, and they all seem to migrate into state 6 by the time they're 30. Similarly, cluster 4 all seem to be in state 0 at age 15, but by the time they're 30 they are all in state number 2. And for state cluster number 2, there seems to be a sort of intermediate period spent in state 0. So everyone's in state 0 to begin with. They all seem to migrate into state 1 and then end up going into different states by the end of the observation period. The one thing to be mindful of is that this is aggregated information at these split by these different time points, and so these aren't actual sequences, and so you kind of lose the uniqueness of the sequences through this aggregation. The next visualization I'm going to go through kind of gets around that sort of loss of information, because it actually plots an actual sequence of information rather than aggregating it. And it's called a medoid, or representative sequence plot. And I'm going to run it and explain it. So again, we're using the sequence object, grouping the visualization by our cluster solution. Because this is a plot of the most representative sequence, we need to feed it the distance matrix, because it needs something, it needs something to calculate the most central sequence. And then this option is just saying extract one sequence, so you can extract multiple sequences in order to get greater coverage of representativeness within each cluster. And if I open the visual, admittedly this is a bit cluttered, and there are methods that you can use just to focus on one of these visualizations for a cluster rather than presenting them in this sort of tessellated thing, but we'll just go with this for now for the purposes of the video. So the way to interpret this is an actual sequence that belongs to someone, and it gives a breakdown of what this person reported they were at each of these 16 time points. So cluster 1, the most central sequence, was being in state 0 between the ages of 15 to 21, and then going into state 6 from age 22 all the way up to last observation at age 30. There is some additional information that you can sort of see here, which is the coverage of this sequence. So it's essentially saying how many other sequences within this cluster are within the vicinity of this most central sequence. And I'm just going to move on to the last visualization. So this visualizes the transitions between the different states. And if you recall, this is sort of similar to how the methodology used to calculate the costs behind our distance matrix. So as before, I'm just going to run it and explain. So I've taken a slightly different approach, and I'll open it up so you can see why. So this is quite a busy diagram, and it obviously doesn't lend itself well to trying to cram 5 other transition matrices into the same plot. So I've used a piece of code in order to just focus on cluster 1. So this is the transition matrix for cluster 1. And if you wanted to produce the transition matrices for other clusters, then you just change the number after this particular piece of code there. This option within the transition matrix plot function is just to make sure that the labels within the diagram don't overlap, and also this particular function means that the transition matrix only plots transitions into a different state. So obviously, if you're comparing two time points, you could remain within the same state between those 2 time points. Using this option means that you only look at instances where someone changes a state. And if I open back that, so essentially the transition matrix compares the state at one given time point, so time point t, with the following time point t plus 1. So you sort of interpret this as if you were in state 1 and you left, then 58% of people left state 1 to go into state 3, and 41% of people left to go into state 6. These figures sum across rows, so it gives you so this is the proportion of people who leave this state at time t, and then where they go at time t plus 1. So that's all the visualizations that I'm going to go through. As I said, the Treminer manual has loads more. You would also probably do some other analysis. So in the worksheet, I show how I provide you with a piece of code that allows you to attach cluster membership to the biofam dataset. So you can then engage in a series of bivariate analyses. So for example, you could look at the distribution of gender by cluster membership, or whatever else is contained within the biofam dataset. So you could look at if there's different nationalities follow different clusters, or different languages follow different clusters. So that's one potential avenue for sort of describing what's going on within those clusters. You may also want to engage in multinomial logistic regression to predict cluster membership. So the interest there would be controlling for a range of characteristics what makes you more likely to follow or to belong to one particular cluster over another cluster.